Are you hearing me?
Yes,
Yes, Doctor.
it's
Okay.
started.
Come on. So let us continue genetic algorithm and also we will see today, inshallah, some of the key parameters of the genetic algorithm and how to set them at the beginning. After discussing this selection, crossover, mutation, and elitism operators, this is the flow chart, and I hope everything is clear on how it, how the GA genetic algorithm is operating. Okay, so let me have this here. Okay, let us take a simple example how the GA works. Assume that you have a large number of XY data points. And you can have like some measurements system. You have input and output. So you have pairs here, X input and output. And okay, so you have these measurements, pairs X and Y. Okay, so what is this? I don't know. I don't, okay. طيب. Okay, so we have these two pairs. For example, you have X equal to 1, then the corresponding Y, XY, XY, and so on. So what is our objective? We need to, curve fitting. We need to find out a function Y as a function of X. So you would like to fit a polynomial of up to degree 5, up to the 5th degree. Of course, this degree can be set. You need to be 4, 5, 6. You can try any degree, and then you can find the best one. So assume that we need to approximate or to do curve fitting up to the 5th degree of X through these data points. We need to find Y as a function of X to minimize or to emulate this value. If we have X equal to this, then this Y equal to the measured value here. So that is you want a formula Y equal to AX to the power 5. This is a degree 5. BX4, CX3, DX2, EX plus F. So the absolute term here. That gives you a reasonably good fit to the actual data. So you have these coefficients A, B, C, D, E, and F. These are unknowns. We need to find these coefficients in order to minimize the error or the best fit to be best fit for these pairs. So in this case, A, B, C, D, E, and F, these are unknowns. These are the optimized parameters. We will play with these parameters A, B, C, D, E, and F in order to minimize the error between the simulated value and the measured value. So these are unknowns. These are the optimized parameters. So these are the genes that we have. So our chromosome will be A, B, C, D, E, and F. So these are the genes, these are the optimized parameters, and this is our chromosome. So, okay, usually to compute the fit, definitely you can define any objective function. Here you can define your performance index. You can say we need to minimize the error between the measured value and the simulated value. So this error could be as such for any particular solution. You have y, I, let us say calculated, minus y, I for a certain value of the x or any value of x, x1, 2, 3, and so on, measured. This is the error. So we can square the error in order to have it positive, whether it is up or down. It doesn't matter, it is an error. So we can square this and we can add this all over the all patterns that we have. We can sum all pairs that we have. So we can get the sum of the errors of each one. So we need to minimize this object. This is our objective function that we need to minimize. Minimize this objective function subject to A, B, C, D, E, F. You can have the range of A, B, C, D, E, F. You can specify the range and check whether it is okay or not. Okay, so this is our optimization problem now. We need to minimize the error between the calculated value based on this function for a certain values of A, B, C, D, E, and F, and the measured value of Y, which is 4.1, 9.5, and so on. So this is our objective, and these are the constraints, and we can go forward. So compute the sum of the actual Y minus predicted Y square. The actual Y اللي هي الميجرد Y اللي هي 4.1, 9.5. The predicted Y اللي هو we are predicting it from here. So this is the calculated or predicted or whatever. The lowest sum represents the best fit. Definitely, if you minimize this, the solution that gives you the minimum error, summation of errors over the whole values of x1, 3.1, and so on. So this is the best fit or the best solution. There are some standard curve fitting techniques, but let us do it by genetic algorithm. Of course, there are some least square method can be implemented here, straightforward for curve fitting. However, let us see the genetic algorithm, how it works. Hopefully, the genetic algorithm as a global optimization technique will give you better solution than the other techniques. Okay, so the genes are A, B, C, D, E, F. Your chromosome is an array or a vector of A, B, C, D, E, F. And your evaluation function for one array or for one solution for every actual value point x and y, I am using red to mean actual value. So you have here, this is the predicted value. This is the predicted value. I don't know. Okay. This is the predicted value for a certain value of A, B, C, D, E, and F. We can compute, and we can. This is using the red in the middle of the, not the actual value, predicted value. So this is impossible. This is the predicted value, and this is the actual value. So find the sum of the error square over all x. So you can take, for any pair, you can take x and substitute and get y prime and compare it with y. And this is the error for this solution and so on. So the sum is your measure of badness larger numbers. Of course, if this is an error, but the larger the error, the worse the solution. For example, if you have these are the genes, this is a possible solution. This is a candidate solution for the problem. This is A, B, C, D, E, F. And the data point is 1. These are the data points, for example. So let us take 1 and substitute here. 0x to the power 5, 0x to the power 4, 0x and so on, x equal to 1. And let us calculate the output here. And we compare it with 12. And so we can get the error. And also we go back and substitute with x equal to 2 and calculate here x equal to 2. You can get the predicted value of y, and you compare it with 21 and 22. So you can get the error between the actual and the predicted value. And then you can continue. For x equal to 1, you have the predicted value equal to 10. For x equal to 2, you have the predicted value equal to 19. So the error here equal to 3 and the error here equal to 2. So the objective function in this case, if this is the solution, okay, if this is the solution, the objective function equal to summation of 2 square plus 3 square. So this is equal to 13. So this solution, and this is the fitness of the solution. If you have another solution, 1, 0, 2, 1, 0, how many parameters do we have? We have 6, 1, 0, 2, 1, 0, 1 for example. طبعا مش لازم 1 و 2 ممكن يبقى 10 مثلا. It depends on the range of A, B, C, D that you specify. Let us 4, this is 4, and this is 7, for example. Then you can substitute. These are with x equal to 1 and they calculate, x equal to 2 and they calculate, and then you can get the summation of errors, and you can get the fitness corresponding to this solution. So if you compare the fitness of this solution and this solution, you can see which one gives you lower error. So this is the better solution. Of course, you generate maybe 50 solutions for the problem. This is the population size, and then you can select for parents and do crossover, do mutation, and if you want to implement the elitism, also you can do, and then you can continue, and hopefully the error will get lower and lower with the progress of the search. Okay, so this is the objective function or the fitness of that individual, which is 13. If these are the only 2 points, so this is the, of course, if you have more points, you can, create the error for each point, and you can get the fitness of each one. Sharif Ibrahim, please, Sharif.
Yes. السلام عليكم دكتور.
سلام.
Doctor, excuse me, the dates, you assume these the points or
Which one?
112 to 22?
Yeah, these are, assume that these are the measurements. You have a plant here, or you have a process here, and this is the input and this is the output. Okay? If you want to do some, if you want to develop a mathematical model for this plant, this is the input and this is the output. Okay? So these are some measurements. You have some measurements here in real life. You can have some measurements for the input and the output. So you have X and the corresponding Y. Okay?
Okay, what about the other points, the other data point 222 in the other slide, in the next slide?
These are just an example. You can extend this to 1 with 12. This is another measurement point.
Okay.
And also 2 with 22, this is another. And definitely you have thousands of measurements here you can have. And these are some examples of the measurement points. 1 with 12 also the measurement point, similar to this one. And this is also some other measurement points. If you have all these points, you can have this summation over all patterns, over all pairs. This summation over all pairs. And you can, here we have only 2 points that we consider here in this example. Now we mentioned, but just for clarification, assume that these are the 2 points that we have. So summation, this summation will be over 2 pairs of points. For x equal to 1, we get the error. For x equal to 2, we get the error, which is 3 here, 19 or 22. If we have 1,000 measurement points, so for x equal to 1, we have 2, and we have here another. So we take x and substitute, and then we take x and substitute, and we sum all the errors. So this becomes the fitness corresponding to this solution. And we repeat this for other solutions and other solutions in the population. So you can, if you have the fitness of each solution, you can, of course, extract the best solution, and you can do the selection and the crossover mutation, and you can proceed further. Is it clear, Sharif?
Yes, clear, doctor. Thank you.
Salim?
Yeah, Professor. Is this another way for system identification and control system if we want to?
Yes.
Okay.
Yes, it's system identification. Al-Fawzan, please. Al-Fawzan.
Yes, quick question, Doctor, here. You made the summation here, 2 square plus 3 square. That's, we take only the x value and we substitute, and then we get the number, the fitness number.
This is for x equal to 1. This is the output. So the error here is 12. This is the actual value, and this is the predicted value. So the error here is 2.
Okay.
And for the second point, you take x equal to 2 and you get 19. So that means the error for this point is 3.
3,
yes. If you have other points, other measurement points, you will go and substitute x and you get the error. And for the 4th one, 5th one. So if you have 1,000 measurement value,
you sum the error over 2,000 pairs and then, or 1,000 pairs, and then we get the fitness.
Exactly. So this becomes the fitness of this solution only. This is the fitness of this solution. You will repeat
Yes.
this process for other solutions in the population. طبعا of course in the population size you have 10, 20, 50 solutions you assume. So you will repeat this for 50 solutions and you can get the fitness of each one. And then you can extract which one is the best solution, and you can do the selection, crossover, mutation over them. Is
Okay.
it clear? طيب.
Yes, yes.
هشام محمد. هشام.
Yes, doctor. Actually, it doesn't mean that the more measurements I have, the more accuracy I can reach.
Yeah, of course, طبعا. Of course, definitely. يعني usually this is the case. The more measurements, so the more data you have, the more accurate identification. Definitely.
The other question here, our objective function to minimize the fitness.
To minimize the error. To minimize the error between the predicted value. You assume انه ال y equal to this. You assume انه ال y equal to this, right? You assume ال A will B will C will D and you, of course, in genetic algorithm you start them randomly. Definitely you have an error between y prime and the actual value. If you take x equal to 1 and substitute here with these coefficients selected randomly at the beginning, you will definitely find y prime different than this y. مش كده ولا ايه؟
Yes.
Our target is to minimize this error. We need to find A, B, C, D, E, F to minimize this error over the whole measurement points. So this is for x equal to 1, you have the output equal to 10. So the error for this pattern only is 2. For this pattern, the error is 3. For the other patterns here, for this one, the error is 5 and so on. So you can get summation of all these errors. We need to minimize this. We need to minimize this error. Okay? So the lower the error, the better the solution. So we repeat this for another solution and we get the error, and the other solution will get the error, and we can rank them, we can know the best solution, and we can select based on these, the parents, and we do crossover and we go forward. We move forward in GA. Is it clear?
Yes, thank you, doctor.
Okay. If these are the only 2 points, so this is the fitness. If you have more points here, then you can continue and you can add error square plus error square and so on until you get the fitness. So this is just an example, how the genetic algorithm can be implemented for this prediction or forecasting or any regression points, regression problem. Okay, or identification, model identification. So this is the case. Nasser Hakami.
Yes, doctor.
Yes, please.
For the genes to make the populations, what is the best criteria? For example, this example, shall I go for the negative or to the positive? Shall I make my range from -20 to 20, or I will just make it from -1000 to 1000? So
here, Nasser, if you don't know, assume that we have no knowledge about the range of A, B, C, D, E, F, right?
yes, that's what I mean.
Okay. In this case, what you can do, you have 2 approaches here. The first one is to have, these values. I would like to have some space to explain. Let me end this, and we come here, and we have new slide, so we can have it here. Okay, so assume that this is generally the case for any other optimization problem, not necessarily this one. You have A, you have A max, and A minimum. Okay, so you don't know at the beginning, you don't know what is A minimum, what is A maximum. So one way is to start with the big bounds. Let us start with minus 1,000 to 1,000. Okay?
Okay.
Then you proceed with the genetic algorithm, and you see at the end, the final value, how much A for optimal solution? How much is this coefficient for optimal solution? You found it equal to minus, for example, 500. For example. So in this case, you can focus more on this region of minus 500. You can, in the second run of GA, separate run, you can have this A optimal between minus 600 to minus 400. So this is A. And you start with GA again. Okay? So you can do some fine tuning. Yani after having this wide range, and you found A is in between, so you can focus more on this area. You can run GA again, but you can change the bounds of each solution. Now, of course, this is A, and also you will do this for B, for C, for D, and so on. طيب, assume that, is it clear?
Yes, doctor, it's clear, but changing the A in the same time with changing the B, it is also different changing the A and keeping the others constants. So because maybe changing the A will change the area of the best solution for the B in the same time.
Could be. It could be. It
Yeah.
could happen. But generally, this is the case. You can start with very wide range, and then you can focus more on the solutions here. This is one way. The second way is you can start with the very low value, and you can have small value. Let us start with minus 10, A equal to 10. And you run GA. If this area or this range is not where the optimal solution locates, you will end up with GA gives you A equal to 10. That means in A, this parameter hits its upper limit. So in the second run, you can relax this 10 more. Okay? So you can extend this to 100, for example, and run. If it hits 100, that means you have to go further. And you can do some kind of extension of the bounds if the solution hits the limits, then you can relax it. Okay, this is another approach, and you can top down or bottom up. You can have either way to find the range of the parameters if you don't have any idea about them. Is it clear, Ya Nasser?
Yes, clear, doctor. Thank you.
Okay. Abdullah Yusuf, please.
Doctor, I have a question. Is the objective function the same as the fitness, or they are different things?
As we clarified this point earlier, the objective function, our performance index, our fitness, They are the same if maximize. Okay. If you are maximizing the problem, so the higher the objective function means the higher the fitness or the performance indexes that you have. If you are minimizing, so the fitness is somehow different than the objective function. The lower the objective function, that means the fitter the solution, but it is opposite to the strict sense of that word, fitness. Okay, especially if you use the roulette wheel selection, which depends on probability, depends on the objective function or the value of the fitness over a summation of the objective here. So here the meaning is contradicting with the objective function if you are minimizing. This probability should proportional to the fitness of the solution, right?
Yes.
So if the solution is the fittest, this will give you the highest probability. طب لو قلنا الفيتنس here is the same as objective function, لا الobjective function if you minimize, the lower the objective, the better the solution. The lower the objective, the better the solution. Is it clear?
Yes, yes.
يعني الفيتنس here is somehow is not equivalent to the objective function. You have to do some transformation between the objective function and to get the fitness. If you use here the roulette wheel. Is it clear?
Yes, yes, clear.
Okay. And for example, if you have solution 1, this gives you the objective function equal to -5. And the solution 2 gives you مثلا 3. If you have a solution 3, it gives you -10. This is the objective function. Okay. So for these solutions, if it is minimization, which solution is the fittest one or the best one? If this is a minimization problem.
-10 maybe.
Maybe يعني ممكن يكون 3 مثلا او -5. لا هو -10 يعني definitely -10. This is the best solution with the minimum objective function, and this is the fittest solution. يعني we can say that this is the fittest solution. Okay. Now it gives you the minimum objective function. Is it clear?
Yes.
Okay. So if it is maximization problem, they are the same: objective, performance, fitness. But in minimization, يعني the meaning of the fitness here is gives you the lowest objective function. I hope this addresses your question. طيب. The key parameters of GA performance. You have some of the parameters that needs from you to set them at the beginning of the search. So what are these parameters? If you still remember, can we list كده the parameters that needs to be set at the beginning?
Population size.
Population size. You have to define the population size, and you have to keep the population size as it is: 10, 20 solutions, 50 solutions, 100 solutions. It's up to you. Of course, you can do some kind of trial and error, but definitely, you can say with lower value. With lower value, what do you think the impact of this compared to the higher value of the population size? A lower value, of course, the computational time will be less, but the convergence in order to reach to the optimal solution may take more iterations. Here, the computational time is high, but you can get the optimal solution with lower number of generations. Okay, so this is the population size. Second, what else that we need to set at the beginning?
The criteria for the selecting the values, where is my best solution will be, where should I stop?
يعني maximum number of generation.
No, I mean, for example, if I'm looking for minimizations, shall I stop when my error is 2% or shall I stop when my error is 5%?
طيب, okay, so the stopping criteria.
My limits, I mean, for the solutions.
The stopping criteria you mean, yeah?
Yes.
Okay, the stopping criteria, of course, where we can stop or when we can stop. So one way to do stopping criteria is to set the maximum number of generations. I will do this procedure of selection, crossover, mutation, and the evaluation of the objective, extracting the best solution, and so on. I will repeat this for 100 generations, for example. If I reach 100, then I can stop. Other, of course, stopping criteria, as we mentioned earlier, you can have the best solution doesn't change for k iteration or k generations. You can say no, if the best solution doesn't change after 10 iteration or 10 generation, I will stop the search. I assume that no, I reach to the optimal solution and no further improvement can be obtained. So I will stop the search here. Sometimes, as I mentioned earlier, we can have what we call the premature convergence. So somebody can say, no, okay, if the best solution doesn't change for k iterations, I might reach to the premature convergence, not the optimal solution. So I have to disturb the population again. So you can say, no, okay, after 10 generation, if it doesn't change, then I will increase the B mutation, or I will inject to the population some random solutions, some solutions created randomly without any variance, without any crossover, without anything, just similar to the initial population. So I inject the population with some of the random solutions. Hopefully, these solutions can, overcome the stagnation point that I have. And then you can, of course, continue until you, this is could be the stopping criteria. What else?
Fitness evaluation.
Fitness evaluation, objective function, you mean?
Yeah.
The objective function, yes, this is a problem dependent. And an objective function, you have to define it. This is from the optimization problem. What we want to highlight here is the key parameters of GA, of the technique. And now, of course, definitely to implement the GA, you need to have an optimization problem. You have the objective function J, and you have subject to some constraints. So this J is problem dependent. It has nothing to do with GA. Is it clear? And you can define any objective function similar to what we have in objective function here, summation of the error square over I. So this is the objective function we need to minimize. So this is the optimization problem. Or this is the formulation of the optimization problem. It has nothing to do with the GA. Am I right?
Yeah, yeah.
Okay. Right. What else, Yusuf Ahmed?
Yes, and maybe we can include the percentage of crossovering and muting as a key parameters.
Yes, of course. Probability of crossover. You have to set it at the beginning. Probability of mutation. You have to set it at the beginning. Okay? So these are also two parameters you have to set. If you still remember in the selection process, where we have two kind of selections, either roulette wheel or the tournament selection. And in tournament selection, we mentioned that the best solution can be can be considered as a parent with 80%, for example. If you still remember this. And not necessarily to consider the best solution as a parent, maybe with 80%, this could be happening. Did you remember this? Did you remember this or not?
Yeah, the statistical perspective for selecting the solution.
Yes, we mentioned that, and we have some probability of the selection probability. Okay, this selection probability could be, for example, 0.8. So the best solution would be considered as a parent, but with 0.8 probability. Crossover probability, as we mentioned earlier, this is between 0.6 and 1. 1 means you have to do crossover. B mutation is very low, between 0.001 to 0.01 or 0.05. Very small probability here. And this is also 0.8 and 1. 1 means you will select the best solution right away as a parent. So this is these are some of the key parameters that you have to set at the beginning. Of course, you can start with, for example, 20 solutions and the crossover equal to 0.6, mutation equal to this, and this B selection equal to 0.8, and then you run the you run the GA, and then you can have several runs. For example, we can say this is the objective function, and this is the number of generation. This is the objective function, our fitness value, and this is the number of generation or iteration. So at the beginning, of course, you will start with initial population selected randomly. But definitely, you have very bad objective function at the beginning, and then with the proceeding of the minimizing this, you will start minimize the objective function. So after 10 iteration or 10 generation, you will see the objective function comes below and below. So this is maybe with the B crossover equal to 0.7. What you can do, you can repeat the process. You can repeat the GA with crossover equal to 0.9, for example. You may find this is the solution. This is with 0.9. B crossover, and so forth. You can do this for B mutation, different value of B mutation, different value of crossover, different value of population size. So maybe this is with 20 solutions. You can run another with 100 solution. This is population size is different than those. And you can usually for these techniques, you can do some kind of initial trials, and in order to set these parameters wisely, and definitely the solution at the end, if your technique is robust, you will end up with the same solution at the end here. If you end up with the same solution here, and you are very lucky, your technique is robust. 0.7, 0.9, it doesn't matter. You reach to the optimum solution at the end. So this could be one way in order to find the optimal set of this. But this is, of course, have to be defined at the beginning of the technique. So the key parameters we need to set. Computation time, definitely, as we mentioned here, computation time depends on the population size and also the initial solutions and all this. Complexity of the fitness. The beauty of these evolutionary techniques, you can define whatever you want as objective function. As we mentioned earlier, in classical optimization, you have to have some restrictions on the objective function. For example, for linear programming, you have to have a linear objective function. You have to have like a gradient. The gradient is defined. You can get the gradient of the function and the constraints. And all these restrictions are not here in evolutionary techniques. You can define any fitness function and you can have any constraints. There is no restriction, as we will see. The generations and the population size, these are the number of generations, and the population size also is some of the key parameters that you have. And population size, crossover probability, you have to set it high, between 0.6 and 1. Mutation probability, this is another key parameter you have to set. Number of individuals in the selections. Here for tournament selection, we select two solutions and to compare among them. Maybe you can have 3 solutions and you compare among them. It doesn't matter. So you have to default to 2, but you can extend, of course, number of individuals in the selection process. A number of elite individuals, if you implement this elitism, so how many solutions will be directly transferred to the new population without passing over the crossover and the mutation process. So this is also should be, this is a key parameter you have to identify if you want to implement this elitism. So you can say 10% of the population. So you rank the population and then you take the 10% right away, or you can define 5 solutions, 10 solutions, and so on. The stopping criteria you have to define, as we mentioned earlier. The parameters must be selected with maximum care. So you can run the technique several times with different probabilities, different approaches of the selection, and so on. So at the end, you end up with the best setting of all these techniques. So GA computing time depends on the complexity of the fitness evaluation, definitely. Objective functions, and penalties, etc. Actually, for this problem, f of x equal to x squared, where x, this is maximized, where x between 0 and 31, this is very simple problem, definitely. The objective or the constraints here are self-satisfied. The constraints are self-satisfied. That means, when we select X in order to substitute here, we select X between these bounds. But this is satisfied. يعني خلاص يبقى هي كأنها unconstrained problem. But in real life, it is not as easy as you can see here. You may have some of the constraints which is not directly related to this X. You have to solve the problem, and then you evaluate the constraints. And if you have some of the violation on the constraints, then you consider another solution and so on, or you add the constraints here as a penalties here in the objective function, like Lagrange multiplier method. So in real life, the problem is could be very, very complicated. يعني the calculation, the fitness is not as easy as we have here. Okay, so complexity of the fitness, of course, will affect the computing time, evaluation, objective function methods, and so on. Number of fitness evaluations. What do you think? Number of fitness evaluation. How many times we will evaluate the fitness if we run a GA from A to Z? If we run the complete, technique from the initialization to objective function evaluation, selection, crossover, mutation, stopping criteria. If no, then go back and evaluate the functions, select, crossover, and so on. How many times that we need to evaluate the objective function?
It depends.
Depends on what?
The solution is satisfy or it's reach the stopping criterion.
Okay. What I want to say here, can we develop like expression and how many times that we are going to calculate the objective function here or the fitness evaluation? And it depends on
how many generation we have.
This is one. How many generation we have? What else?
Also individuals.
Number of operations.
Low population size. In population size, you have 100 solution, and this population size is repeated for 1,000th generation, for example. So in this case, for each solution here, you have to evaluate the objective function and overall the number of iterations that we have. So this is simply the number of individuals in a population, the population size in a generation, multiplied by number of generation. This gives you the number of fitness function evaluation. So you can now, if this is, for example, 50 solution, and you run this for 100 generation, so that means you will calculate the objective function 5,000 times. So of course, this will affect the computing time. If you have any question, please raise your hand. Complexity of fitness, evolutionary computation model. Hisham?
Yes, doctor. Actually, this is the number of fitness evaluation as per this expression. Is it the maximum number?
Not the maximum number. Actually, if you have, but يعني definitely this is the minimum number. Let us say this is the minimum number. Okay, and this is the minimum number of evaluation. It depends on your implementation. For example, if you still remember, in crossover, you have parent 1, parent 2, you do crossover, you have a child 1 and the child 2. Right?
Yes.
In some cases, we mentioned that we need to evaluate the children objective function, and we can select between parents and the children in order to copy for the new population here. And we will not use the children directly to the new population, but we can select the best 2 out of 4. So in this case, you need to evaluate also the objective function corresponding to this child, right? And then you compare. Is it clear?
Yes.
So in other words, you can have also the when you solve the problem, as I mentioned, in real life, you can have so many constraints, and you have here the when you have any solution, and you can calculate this, and you may find out here the constraints are violated with this value. So in this case, you have to get another solution and so on. So this is let us say the minimum. This is the minimum number of evaluation. In some cases, in some crossover also, you can have more than child. You can have 3 child out of 2 parents. As we will see later on, you can generate 3 child out of the 2 parents. And in this case, you have to evaluate, and then you select 2 of them, or you select between parents, and definitely you can have more evaluation of the fitness function than this number. Okay? So this is the minimum number of fitness evaluation.
Sorry, doctor, I wanted to ask this question. Does number of generation represent the number of iteration?
Yes. Yes.
Okay. Is it necessarily to do all iteration, or we can stop once we satisfy with our objective function?
This is the stopping criteria. This is the stopping criteria. This is the stopping criteria. This is one generation or one iteration. Okay, one iteration or one generation. Crossover, mutation, population, and then you evaluate. خلاص, now you complete one generation. احنا بنسميها في الجينيتيك algorithm literature, we call it generation, but here it's similar to the iteration in any other technique. So since the genetic algorithm emulates the human being, if you have parents and then children, and this is the first generation, and the children will go as a parents, and then you have other children, so you have a generation after generation, but they are the same. Is it this is your question, Sham?
Yes.
Okay.
Thank you, doctor.
Of course, you can stop the search if you are satisfied. As we mentioned here, the stopping criteria, you can have the stopping criteria Again, you can stop either you reach to Gmax, maximum number of generation. Best solution doesn't change over K generation. You can stop whenever you reach to a satisfactory solution, a satisfactory solution. And you can say no, if the error مثلا الerror اللي احنا يعني in that example when you have the error over the E square, if this error is less than epsilon, then you can stop the search. You are satisfied with this. If the objective function, for example, is a distance, so the minimum distance is 0. If you reach 0, خلاص يعني no need to do any further research. If the distance becomes 0, for example, in control methods or in control problems, you can do the following. You can have this is j omega, and this is sigma. This is the S plane. So you can say no, our eigenvalues somewhere here. These are the eigenvalues of the system. The system becomes unstable. So we need to design a controller to shift these poles to the left. You can say no, okay, I will stop if this x go to the left of this line. So this is this is the line where we have here this is sigma. This is the you have here a certain sigma. So the of this eigenvalue shifted somewhere here, you can solve the search. You don't need to if it crosses this line, yeah, but you have a satisfied solution and you can stop. Or you can of course you can either eigenvalues or real part of the eigenvalues, or you can also work on the damping coefficient. If the damping coefficient is greater than 0.5, I will be satisfied with this damping, and I can stop the search here. Okay, so if you reach to a satisfied solution, satisfactory solution, then you can stop the search. Okay. Okay. We have a very simple quiz, but let us continue, finish. Hopefully, EC models may be as complex as necessary. As we mentioned, we don't have any restriction on the objective function or constraint. Could be any discrete, non-discrete, continuous, non-continuous, smooth, non-smooth, whatever. Multiple objectives are treated in a natural way. Of course, you can extend the genetic algorithm. Later on, we will discuss this point to have a multi-objective optimization, evolutionary computation, multi-objective optimization approach for the evolutionary computation, which is, of course, definitely, you don't need to aggregate all the functions together. A function with a many local optima or non-connected domain may trap classical search method. As you mentioned here, if this is your, if this is your function, and for the classical technique, you start at this point and you calculate randomly, you select this point and you calculate the gradient. You will go this way and then this way and then this way, and then you come trapped at this point. But for evolutionary computation algorithms, it works with the number of solutions, and these solutions are scattered over the search space. So you can have this, if this is the case, and you can have jump here, and you can reach to the optimal solution at the end. So this is one way. Generations and the population size compromise in the number of individuals and the possible number of generations must be arranged. A too small population may lead to slow convergence or no convergence. If you have very small population size, if you say in the population size, for example, equal to 10, you may experience non-convergence. Now these 10 solutions, if this is a search space, these 10 solutions are scattered here in this point. Maybe the global optimal solution here is somewhere here. But if you have a higher number of population, so you select solutions here and there, so hopefully you can reach to this optimal solution. So too small population may lead to not convergence, let us say. Parallel computation drastically reduces computing time. If you have some hardware facility to implement this in parallel, of course, you have here population with 100 solutions. You can scatter them 50 in this processor and also the other 50 in this processor, and then you can combine them. And of course, you can have some parallel computation to reduce the process. So by this, we finish the GA. And let us give you the quiz. It's a very simple quiz. Just 2 or 3 minutes. It will not take more than this. Make it available now. So 4 minutes. Okay. So it is now you can start the quiz, and this is for 4 minutes, and we will come back. I think the time is over. Okay. So let us continue. Yes, Nasser Hakami, do you have a question? Nasser.
Sorry, I was on mute. I have question in the elite. In the elitism, we are selecting a special answer that we believe it is the good, that does not need to be changed. It should go to the next generation.
Yes, you're right.
Yeah, so if, for example, I'm making 5 generations. So if I select, for example, a 5 out of 2 out of 10 in the first generation, shall this one continue until the end, or each round I should select, I make the elitism criteria repeated again, and I should select maybe the children become one of the elitism?
Yes, you are right. You have to select. You have initial population. You select 2 of them.
Yes.
When you have children and all the new population, you select 2 of that population.
Of the new one.
Of the new one. Maybe
so
the others one already disappear, and we have some children better than them. So you can replace. At each iteration, you select from the iteration itself.
Okay.
It is not taken for credit. Definitely for each generation you select the best solutions. Okay?
Okay, Doctor. Thank you.
So any other question? Okay. So here we have another question here, Muiz.
Doctor, I want to ask about the encoding. Actually, do we assume only integer variables? Because to encode an integer means the binary can only encode integer values, isn't it?
For binary, yes, you have to have this 0 or 1s for each bit, right?
Yes.
But we will discuss after this part, which is the control problem. After this part, we will have what we call the real coded, the second type of the احنا قلنا في binary coded and the real coded GA.
Okay.
You see the real coded GA when you have the genes similar to that problem. We have A, B, C, D, E, F. So these are real numbers. How to proceed with this? How to do crossover? How to do mutation over this real number or real coded GA? This is after this part of the control problem. Okay? We will discuss it. Okay. Okay. So this is the control problem. The idea behind this part is to give you a platform that we need to implement on GA and whatever techniques that we will consider later. We have a standard problem and we implement all the techniques over this problem, which is the controller design. And we will see the how this optimization can improve the stability of the system. Okay, so we will describe the problem, and we will see the open loop stability. And we have very simple problem, very straightforward. We will not go in details about the physics behind the problem, but we will give you standard control problem, x dot equal to ax plus pu. And we need to design a controller in order to improve the stability of the system. So we will see the open loop system stability, eigenvalues of A, and we will see the controller structure. And then we add the controller to this open loop system, and then you have the closed loop system, and you can check the stability of the closed loop system. And in this case, you can, of course, you have to design the controller here, and then you check the system stability. Time is over. Let us stop here. We'll continue next class, inshallah. Next class,